Hello everyone, welcome to Math 115 College Algebra. So in this section 3.4, I want to talk about composition of functions. So there's many ways that we can combine functions together. So I'm going to review those first, and then we'll talk about a new method where the output of one function is used as the input to another function, and that's the composition. So before I get into compositions, let's review like some basic operations with functions. So if you look at this example here, let's say you're given two functions. F of x is x squared plus 2x. G of x is 6 minus x squared. And in part A here, I want to add the two functions together evaluated at a general x. Well, the way to interpret this is this really means this is the same as f of x plus g of x. Okay, so f plus g evaluated x is the same as f evaluated x plus g evaluated x. So literally, to combine them by adding, I just have to add these two functions together. So the f of x was x squared plus 2x. And then g of x was 6 minus x squared. So then I would combine like terms. And actually, in this case, I have 1x squared minus 1x squared. The x squares cancel. And I'm just left with 2x plus 6. Okay, what about, let me do this one first. F minus g. Well, as you can imagine, this just means f of x minus g of x. Right, so again, I start with the function f, x squared plus 2x. You have to be a little careful. I want to subtract the entire g of x. So I'm going to put it in parentheses, so minus parentheses, 6 minus x squared. If I change the signs, or the best way to think about it is distribute into -1 here, I'm going to have x squared plus 2x minus 6 plus x squared. Then I combine like terms. I'm going to get 2x squared, right? X squared plus x squared, 2x squared, plus 2x minus 6. Okay, so that is actually f of x minus g of x. And then so if I go to C here, this means multiplication, right? So this is f times g of x. Again, you could probably guess this. The way you interpret this is f of x times g of x. So if I start with f of x, x squared plus 2x, and I multiply by g of x, 6 minus x squared, I can simplify this by foiling this out, right? So x squared times 6 is 6x squared. Then I have x squared minus x squared times negative x squared, which is negative x to the 4th. Then I have 2x times 6, which is plus 12x. And then 2x minus x squared, which is minus 2x cubed. So that's the answer, but usually put it in descending order, right? The highest exponent first, right? The highest power first. So I'll write this as negative x to the 4th minus 2x cubed plus 6x squared plus 12x. Okay, and then finally, if I divide the functions f divided by g evaluated at x, again, the way you interpret this means f of x divided by g of x. And you have to be a little careful on this one. This is like provided that g of x is not equal to 0, right? Because we can't divide by 0. So in this case, this would simply be my f of x, which is x squared plus 2x, divided by g of x, 6 minus x squared. And you could leave it like that. I guess we could factor out an x from the numerator. So I have x times x plus 2 over, and I can't really do much with the denominator, just leave it as 6 minus x squared. Okay, so that would be the answer. Again, as long as the g of x is not equal to 0. So I guess if x happened to be square root of 6 or negative square root of 6, then that would make the denominator 0. So square root of 6 and negative square root of 6 is not going to be in the domain of this function where you divide the two original functions together. Okay, so those are like the usual ways to combine functions. The new way is called a composition. So how does a composition of functions work, and what does that mean? So basically, when the output of one function is used as the input to another, that's called a composition of functions. And the notation is f, and there's like a little circle here. So f circle g, you read this as f composed with g evaluated x. And the best way to think about it is this is f of g of x. So g of x becomes the input to the f function, right? Think of like g of x as the inside function, f is the outside function. Okay, and so you would read this as f composed with g of x is equal to f of g of x. All right, we can think about this in terms of diagrams. So here's a diagram that sometimes people use. Let's say we have, I'll just draw like a blob here, which represents the domain of G. Okay, so this is like basically our x value. And that's going to be mapped to the second blob, which is going to be the range of G. Right, so some value in here is like the input. So this is our G function, let's say. And then it's going to be mapped to a value in here, which is our output. So this is like our G of x. Right, so again, x is input, G of x is the output, right? So it's in the range of G. But then that value becomes the input to another function, f. So I'm going to have another function, f, where g of x is now my input, and my output will be f of g of x. Right? G of x is my input to my f function. So another way of thinking about this range of G is also equal to the domain of f. And then the final value here is really the range of f, right? The f of g of x. All those values would be in the range of f. Provided that the values make sense, right? Because we could have a g of x that is actually not in the domain of f. It could be fine, like x could be in the domain of g of x, so g of x is fine, but it may not be in the domain of f because you're dividing by 0 or taking the square root of a negative value, that sort of thing. And we'll talk a little bit about that. I'm not going to get too much into that, but we'll talk a little bit about like how to find the domain of a composite function a little bit later. Okay, so let's simplify some composite functions. Let's say I have this. I have two functions, so f of x equals x minus 1, and g of x is x squared minus 1. And I want to find the composite function, which is f of g of x. And then I want to do it the other way around. I want to find a composite function that's g of f of x. All right, so how do I do that? Well, the inside function, right, is like the input, and the outside function, the f, is the output in this case. So I would go to my, here, let me write this down. So I want f of g of x. So I go to my f function, and where I have an x, I'm going to plug in this entire g of x expression here. Right? So where I go to my f function, and where I have an x, I'm going to plug in, the first term is an x, I'm going to plug in this entire g of x. And then you can simplify it, right? So x squared minus 1 minus another 1 is basically just x squared minus 2. So that would be the answer. And in g of f of x, now f of x is like my input and g is my output. So now I start with the g function. Let me write this down again. And where I have an x in the g function, I'm going to substitute in f of x, this expression. So this is going to be parentheses, right? X minus 1, because that's my f of x. But now I need to square it and then subtract 1. Okay, and then you can expand this out. So remember, this just means x minus 1 times itself. I'll FOIL this out, which is going to give me x squared minus x minus another x plus 1 minus 1. And then if I simplify this, I'm going to get x squared minus 2x, I guess, right? And the 1 and minus 1's cancel. And then you could factor out an x if you wanted. So x times x minus 2. So that would be the composite function g of f of x. Okay, a few more examples. Let's say now that f of x is 2x plus 1, g of x is 3 minus x. They're both like linear functions, right? And I want to find f of g of x. So f of g of x. So I go to my outside function, and where I have an x, I'm going to substitute in g of x. So where I have an x, I'm going to plug in 3 minus x. I'm going to simplify this. Distribute into 2, so I have 6 minus 2x plus 1. And then this is just going to be negative 2x plus 7, I guess, here. Okay, and then g of f of x, I'm going to start with the outside function, 3 minus x. And then where I have an x, I'm going to plug in. And again, I would use parentheses, right? Minus, it's the whole quantity f of x, right? Because where I have an x here in my g function, I have to plug in this entire expression, right? So I want parentheses 2x plus 1. Then to simplify it, I'll distribute in the negative 1. So I have 3 minus 2x minus 1. And then I can write this as negative 2x, and then 3 minus 1 is 2, right? Again, you could factor out a 2 or a negative 2. If you wanted to, right? I could say, let me factor out a negative 2. Then I'm left with x minus 1. Okay. Let's see if we can interpret what a composition means in terms of words, right? So this is sort of like a more practical example, and we're just trying to interpret it, like what it means. So example 4 says, the function c of s gives the calories burned completing s sit-ups, right? So s sit-ups is the input, c is the calories burned, that's the output. And the function s of t gives the number of sit-ups completed in t minutes. So t is the input, s is the output. And we want to interpret, what does c of s of 3 mean? Okay, so let's focus on the 3, right? The 3 is the input to the s. And remember, the 3 is the time in minutes. So s of 3 must be the number of sit-ups completed in 3 minutes. So number of sit-ups completed in 3 minutes, right? Because t is 3. Okay, so now that the number of sit-ups completed in 3 minutes becomes the input to the c function, which tells us the calories burned, right? So the way to interpret c of s of 3 is this is going to be the number of calories burned basically after doing sit-ups for 3 minutes. Okay, so the number of sit-ups was now the input to the calorie function, and that gave the output was the number of calories burned. Okay, we can also look at composite functions in terms of tables or in terms of graphs, and we'll do both of that in some examples coming up. So let's start with this one right here. So I have a table. The x is the input to both of the functions, actually, right? So x is the input, and then here's the output f, right? F of x, and then here's the output g of x. So what I want to find is a couple of compositions here. I want to find f of g of 1. So let me start with the inside function, g of 1. What is g of 1? Well, g of 1, if we look in the table here, right? So the input is 1, the x is a 1. What is the output, the g? It's a 3. So this g of 1 here is basically 3. So that means I ultimately want to find now f of 3. The 3 now becomes the input to the f function. So how do I find that? Well, I look back on the table here. If the input is a 3, what's the output to the f function? It's also happens to be a 3 in this case. So this is going to be equal to 3. Okay, what about g of f of 4? Okay, so first, 4 is the input to let me start with the inside function. 4 is the input to the f function, right? So I go to 4, I go to the f function. What's the output? It's a 1. So basically, this f of 4 is equal to 1. So now I want to find, that means I want to find g of 1. So if 1 is the input, what's the output to the g function? It's a 3. So this is also equal to 3. Okay, so these are like functions of functions. All right, let's do something similar, but now using graphs. So I'm given two graphs. The one on the left is the f, right, as a function of x, and the one on the right is g as a function of x. And I want to find several things. I want to find f of g of 5. I want to find g of f of 0. Then I want to find f of 6. So the output to the f becomes a new input to the f function. And then same thing with g of 3. Okay, so in order to solve these, again, I have to evaluate the inside function first, right? So let me start with the one on the upper left. G of 5, what is g of 5? Well, I go to the g function, the input is a 5. What's the output? It looks like it's also a 5, right? So in this case, this g of 5 here is just a 5. So now ultimately that becomes the input to the f function. So now I want f of 5. So I go to the f function where I have an input is 5. What's the output? The output is 0, right? So this is just going to be equal to 0. Okay, what about g of f of 0? So now I go to the f function. The input is 0. What's the output? It happens to also be 0. So this f of 0 is equal to 0. So now I want g of 0, because 0 becomes the input to the g function. So I go to the g function, go to 0. What's the output? The output is a 2. So this is equal to 2. Okay, what about f of 6? So now I'm going to stay with the f, right? I first need to find f of 6. So I go to 6, the input's a 6. What's the output? The output is a 2. So then this is going to simplify to f of 2. And then I go back to the f function. If the input is 2, what's the output? The output is a 1 here. So this is equal to 1. And then g of 3, now I stay with the g function. G of 3, let's see, if the input's a 3, the output would be a 4. So this is equal to 4. This one, let me just write it so I have it. Just remember that was 2. So now I want g of 4. So I go back to the g function, go to the 4. What's the output? Looks like it's a 2. So this is going to be a 2 here. Okay, so again, they're just functions of functions, but now we're using graphs. All right. We can also do this with the equations, right? Algebraically, for sure. So let's do a few examples of that. So let's say, so we did this already with tables. We did it with the graphs, right? Evaluating a composite function at a particular point. There's actually a couple of ways you could do this. So I'm given two functions, right? F of t is t squared minus t, and h of x is 3x plus 2. And I want to evaluate these functions, f of h of 1, h of f of 2, and h of f of negative 2. Probably the easiest way, because we could find the composition first and then plug in the original input. But I think it's easier to do it this way. Let's find h of 1 first. Right? So if the input is a 1 to the h function, what is the output? Well, I go to the h function where I have an x. I'm going to plug in a 1. So it looks like it's going to be a 5, right? 3 times 1 is 3, plus 2 is 5. And now that becomes the input to the f function. So now where we are using a different variable here, we're using t. So where I have a t, I'm going to plug in a 5. So this is going to be, I guess, 25 minus 5, which is 20. Okay, for the second one, let me find f of 2 first. So I go to the f function, and where I have a t, I'm plugging a 2. So this is 4 minus 2, which is 2. And then I want h of that, right, of 2, because that 2 now becomes the input to the h function. So where I have an x, I'm going to plug in a 2. So this is going to be 6 plus 2, which is 8. And then finally, h of f of negative 2. So I really want to find f of negative 2 first. So I go to the f function. Where I have a t, I plug in negative 2. Just be careful with the order of operations here, right? So negative 2 squared means negative 2 times negative 2, right? So this is positive 4. But then I have minus a negative 2, which is plus 2. So this is just going to be 6. And then that becomes the input to the h function. So where I have an x now, I want to plug in a 6. So this will be 18 plus 2, which is 20. These equals should really be on the left side. Okay. So pretty straightforward, right? The output of one function becomes the input to another function. All right, let's do one more example with a table, and then we'll talk a little bit about how to decompose composite functions. Like, given a function, can we find the two functions that were combined to actually make the original composite function? But let's do one more example with a table first. Okay, so here's the table. I want to find f composed with g at negative 1. Well, remember what this means. This means f of g of negative 1. So I really want to find g of negative 1 first. So if my input is -1, what's my output to the g? It's -3. So this is really, the g of -1 is really -3. So this is the same as f of -3. And now if the input is a -3, what's the output to the f function? It's a 1. So this is just equal to 1. Okay, what about g composed with f evaluated at 5? Well, this is the same as g of f of 5. So let me start with the inside function. What's f of 5? Well, when the input is a 5, the output is a -4 to the f function. So this is just -4. So that means I really want g of -4. So if the input is a -4, what's the output to the g? It's -4. Happens to be also -4. Okay, what about f composed with f evaluated at 7? Well, this is the same as f of 7. Right, and it's much easier to write it in this. I think it's easier to interpret it this way. So f of 7, right, is the input to the f function again. 7's the input to the original f function, and then f of 7, the output, is now the input to the f function again. So what is f of 7? Well, when the input is 7, the f is a 2. So this is just a 2. That means now I want f of 2. So when the input is a 2, the output to the f is a -3. Okay, and then finally, g composed with g evaluated at 2 is g of 2. So what is g of 2? Well, if the input is a 2, the output g happens to be a 2. That's nice, and that tells us g of 2 again is going to be, happens to be 2, right? So g of 2 just happens to be 2 in this case. Okay, so again, now let's look a little bit about how to decompose a composite function. So we combine two functions, right, into a by using composition into a composite function, but can we go the other way? Can we start with a composite function and decompose it into two functions? And usually there's many ways of doing this, but there's some that are more obvious than others. So let's say we're given this function h of x is 1 over x plus 5. Can it be expressed in the form of a composition? So h of x equals f of g of x, where g of x they're giving us is x plus 5. So what they're asking is, what does f of x need to be such that that composition is correct? All right, the h of x is f of g of x. We're given g of x, we're trying to figure out f of x. So what must f of x be such that if I plug g of x into it, I get 1 over h plus 5? And it makes sense that if f of x is 1 over x, that will work, right? Because then if I do f of g of x, I go to my f function, and where I have an x, I'm going to plug in g of x, but g of x was x plus 5. And that's the same as our original function h of x, right? So that is one way of doing this. In fact, in this case, it's the only way. So, sometimes if they don't tell you what one of the functions are, there might be multiple ways of doing it. All right, here's another example. So they give us a function, h of x. It's x plus 4 to the 6th power. Can we write h of x as a composition of f and g? So f of g of x. If f of x is x to the 6th, what must g of x be? Well, again, if I go to the f function and I plug in g of x, that's got to give me f of g of x. So in this case, if g of x turns out to be x plus 4, that will work, right? Because then I have f of g of x, I go to my f function, and where I have an x, I'm going to plug in x plus 4, but that's our original h, right? So that's what that's what g had to be in this case, right? So that checks. So in this case, we're looking for what g of x had to be. In this previous case, we're looking for what f of x had to be. Okay. In this last example, we want to write this function as a composition of two functions. Again, there may be many ways of doing this. Actually, to keep things consistent, I call this f, but let me call it, it's probably better if I call it h, right? So let's say this original function is h of x, and I want to find f of x and g of x such that h of x is equal to f of g of x, right? Is a composition of the two. Well, think of it this way. What if I let the outside function, the f, be the square root of x? And then whatever g is, if I plug g into my f function, can I get h? Yeah, if I let g equal 5 minus x squared. Right? Because then I go to my f function, and where I have an x, I'm going to plug in my g function. And that's exactly what we started with. That's what we called the original function h. So these two functions will work, right? If f of x is the square root of x and g of x is 5 minus x squared, then if I do f of g of x, that'll give me that composition. That'll give me the h function. Okay, and then I just want to spend a little bit of time. We'll just do one example here, talking about the domain of a composite function. Domains can be tricky when you have composite functions. So I just want to spend a little bit of time talking about this. All right, so let's say, let me go to the next page here. So if you look at the definition of the domain of a composite function, it says the domain of a composite function, f of g of x, is the set of those inputs x that are in the domain of g, for which g of x is in the domain of f. So, and there's actually multiple ways of doing this, but one way of finding the domain of a composite function is first find the domain of g, then find the domain of f, and then find those inputs x in the domain of g for which g of x is in the domain of f. So basically, we're going to exclude the x's from the domain of g, for which g of x is not in the domain of f. This will make a lot more sense with an example. And again, I'm not going to focus on this too much in class. I'm just going to do this one example on this. Okay, so we're given two functions. F of x is 5 over x minus 1, right? So it's like a rational function. And another rational function, g of x, is 4 over 3x minus 2. And we want to find the domain of f of g of x. Okay? We can actually find f of g of x too by evaluating it algebraically, but we just want to find the domain. So one way of doing this, first find the domain for g, the inside function. So ultimately I want this, right? I want to find the domain of f of g of x. So first, let's find the domain for g. Okay, so what are all the x's that will work for the g function? Well, the only issue we're going to have is we can't divide by 0, right? So that means I'll say we can't divide by 0, right? That's our one issue that we could potentially have. So we need to figure out for what x makes that denominator 0, and then we know x, whatever that x is that makes it 0, cannot be in the domain of G. Okay, so the way to do that is set that denominator equal to 0 and solve it. So we're going to set 3x minus 2 equal to 0 and solve it. So I'm going to add 2, and then I'll divide by 3. So it looks like when x is 2/3, that denominator is 0. So therefore, x cannot be 2/3, right? Because the g function, I can't divide by 0, and if x is 2/3, it's going to make that denominator 0. So 2/3 is eliminated from the domain, right off the bat. All right, now there might be more restrictions here. So now we want to find the domain for f. Well, again, the problem is going to be, since it's a rational function, is we can't divide by 0. So that means if I set the denominator of the f function, which is x minus 1 equal to 0, and solve it, that means x, so this is saying x cannot equal 1. But what is the input to the f function? It's g of x, right? So I'll say, but the input to the f function is g of x. So basically what this is telling me is that g of x can't equal 1. So g of x can't be 1. So what x makes g of x 1? That's going to be another restriction. All right, so basically what we can do is we can set g of x equal to 1 and solve it and see what x makes that. So we're going to set g of x equal to 1 and solve to determine what x makes this true. All right, so g of x was, what was it, 4 over 3x minus 2. We want to set that equal to 1. Is that correct? Let me just double check that. G of x is 4 over 3x minus 2, yeah. Okay, so how do I solve this? Well, I can multiply, I guess, both sides by the lowest common denominator, which is 3x minus 2. So I have 3x minus 2 times 4 over 3x minus 2 equals 1 times 3x minus 2. On the left-hand side, 3x minus 2's cancel, so I have 4 equals... The right-hand side, I can distribute in the 1, which doesn't do anything, right? So this is 3x minus 2. Then I'm going to add 2 to both sides, so I have 6 is equal to 3x, and then divide by 3. So it looks like if x is equal to 2, then that's going to make g of x equal to 1, right? Which makes sense here. So x can also not be equal to 2. Right? Because if x equals 2, it makes g of x equal to 1. And you can check that by plugging. If I plug in a 2 here, 6 minus 2 is 4. 4 divided by 4 is 1, right? So that's true. But 1 can't be an input to the f function, because otherwise I would divide by 0, right? I can't have a 1 here. So therefore, x cannot be equal to 2. And then we already had a restriction for the g function originally, where x couldn't equal 2/3. So x basically can't be 2 or 2/3. Those are the two restrictions for the composite function. Okay, so I'll write that here. So therefore, for the composite function, x can't equal 2/3. We get that from the beginning, right? Because that was not in the domain of g. And then also, x can't equal 2, because that made g of x equal to 1, and 1 is not in the domain of the f function, right? This is what I'm saying. This can get confusing at times. So how do I write this in interval notation? So all other x's will work. I want all other x's, but x is not equal to 2/3 and not equal to 2. So the way to write that, right, for the domain is I can start at -infinity. I can go all the way to 2/3, but not include it, right? Not include that endpoint. Union, go from 2/3 all the way to 2, not include it, union, and then go from 2 all the way to positive infinity. And that'll be all real numbers except 2/3 and 2. Those are like the two restrictions. Okay, that's all. I just wanted to touch a little bit on how to find the domain of a composite function, but it can be tricky. There are other ways of doing this as well, but they're also tricky. All right, next time we're going to talk about one more section in chapter 3. We're going to talk a little bit about inverse functions. Great, thanks.